In this lesson, we're going to explore exponential and logarithmic integration. We'll begin with exponential integrals, and we learned that the derivative of the function e to the x was e to the x. And if we reverse this process, it should be no surprise that e to the x is its own integral as well. And that certainly is the case. So the integral of e to the x dx is e to the x plus c. The one that might not be quite as obvious is the integral of a to the x dx. So if you have any other base besides e, it's still its own integral, but you divide by 1 over the natural log of a. The reason is based off of being able to rewrite a to the x as something base e. So for instance, using inverse properties of logarithms, I can say e to the natural log of anything is just itself. So a to the x is the same thing as e to the natural log of a to the x. And if I did that, then what would happen is, using properties of logarithms, this x can come out as a constant multiplier, and I can make this the integral of e to the x natural log a dx, which is almost able to be integrated, but I might need to use some substitution. So let u be that x natural log a for the exponent, so that du is just the natural log of a times dx. But since no natural log of a factor exists in the original problem, I divide the natural log of a over. So that gives me 1 over the natural log of a du is equal to dx. And I think you can probably see where this is going if you recall substitution well enough from the previous lesson. So effectively, and I think I'm going to come over to this side since there's plenty of open space here, I can now say the integral of e to the x natural log a dx can be written as, all right, so x natural log a becomes u, so e to the u, and dx becomes 1 over the natural log of a du. So effectively I have 1 over the natural log of a times e to the u du, which can be 1 over the natural log of a e to the u plus c. And that was 1 over the natural log of a e to the x natural log a plus c, which looks still kind of complex, but if we work backward, you know, we said over here basically that e to the natural log of a to the x was the same thing as e to the x natural log a, which was the same thing as a to the x. So we can work backwards as well and say this is 1 over the natural log of a times a to the x plus c. And that proves the rule. Now, let's do some examples. Most examples you're going to run into probably won't involve bases other than e. So you should know the rule for other bases, but the more imperative one to be able to perform is base e exponentials. Most of the time when you're substituting, what you want to choose for your substitution factor is the exponent itself, if it's anything other than just x. So if we let u, in this case, be negative 2x cubed, then du would be negative 6x squared dx, which is close to what we have, but not quite. So I need to divide both sides by negative 6. That will cancel this negative 6 out, and I can say that negative 1/6 of du is x squared dx. So this is going to become negative 1/6, x squared dx will get replaced with that du, and then e to the negative 2 x cubed will be e to the u. The integral of e to the u is itself, so this would be e to the u plus c, and because this is not a definite integral, I'm going to switch back to the original variable, which is x. So negative 1/6 e to the negative 2x cubed plus c. Here's another example. The integral of e to the x times 3e to the x minus 2 quantity squared. Here, if I allow u to be the part inside the square, it would be 3e to the x minus 2. Now, normally, we would generally choose whatever the exponent is if an exponential equation exists. But the clue here that that's not going to be the case is that the exponent is just x in these exponential functions. So that's not going to help us any if we do that substitution. Du would now be 3e to the x dx, or 1/3 du equals e to the x dx, which matches exactly what's left over in that integrand. So 1/3 comes out front, e to the x dx get replaced with the du, and then 3e to the x minus 2 gets replaced with u, but it'll be u squared. So 1/3, if I increase my exponent by 1 to integrate u squared, that becomes u cubed, divided by 3 plus c, or 1/9. The variable u is going to be 3e to the x minus 2, and that's going to go to the third power, then plus c. Now let's look at some examples after exploring logarithmic integration. So if you approach an integral that's a rational function and substitution does not apply, then another technique that you could possibly use is logarithmic integration. Generally, things involving logarithms tend to seem like they're getting much more complex, but with this logarithmic integration, it's actually kind of nice. This is a very straightforward method. The definition here, we're still just working off of the rule that we stated already. The integral of 1 over x dx is the natural log of absolute x plus c. We just happen to be extending it so that we're using u substitution. So effectively, if the numerator is the derivative of the denominator of a rational function, then we end up just taking the natural log of the absolute value of the denominator, and that's our answer. More formally, we generally write it as the integral of 1 over u du equals natural log absolute u plus c. But I kind of like this second form here in terms of how I actually work these through. So let me show you some examples. So for instance, in this example, I have the integral of 4x minus 3 divided by 2x squared minus 3x. The derivative of the denominator would be 4x squared, or 4x minus 3, because if I let u be 2x squared minus 3x, then du would be 4x minus 3 dx. In the substitution process, what happens is 4x minus 3 dx all gets replaced with du. The denominator is just u. So I'm integrating 1 over u du, which is the natural log of the absolute value of the denominator, plus c, which is the natural log of the absolute value of 2x squared minus 3x plus c. So effectively, right from the beginning, if I notice that the numerator is just the derivative of the denominator, the answer is going to be the natural log of the absolute value of the denominator. Here's another example. The integral of 1 over 3x minus 1 dx. So if I let u be the denominator, that's always what would have to be the case in these logarithmic integrals, then du would be 3 dx. It's not exactly the derivative of the numerator, or the numerator is not exactly the derivative of the denominator, but it's only off by a constant. And as we've seen, we can handle these constants. So you can either choose to walk through the steps and make all the substitutions, or you can just say this is going to be 1/3 times the natural log of the absolute value of 3x minus 1. Oops, I need another absolute value bar there, plus c. You can show it if you're uncomfortable with that. You can go through the steps. So put your 1/3 on the outside, then you have 1 over the 3x minus 1 becomes u, and dx is the 1/3 du. Integrating this results with the natural log, so absolute u plus c. So we get 1/3 times the natural log of 3x minus 1 plus c. So even if you just check first and set up that constant that might be off by a little bit, you can still do these examples pretty quickly, just knowing if the numerator is pretty much the derivative of the denominator, it's just the natural log of the denominator. Here's another example. The integral of x squared minus 2 over x cubed minus 6x. So the denominator is x cubed minus 6x. The derivative of that would be 3x squared minus 6 dx, which if you divide everything through by 3, that would give you 1/3 du equals x squared minus 2 dx. And that matches the numerator. So all we need to do is say this is 1/3 times the natural log of the absolute value of the denominator. And again, if you're uncomfortable with that, go ahead and fill in the steps and prove it to yourself. Now, if you'll notice, the logarithmic rule is going to work in the case of rationals when the numerator is 1 degree less than the denominator, in general. It doesn't always have to work that way, but that's when it's going to work. But there's also different cases where it can still work for improper rationals, and an improper rational means the degree in the numerator is higher than the denominator. But you must perform polynomial division. Improper rationals are rationals where the I just said that. I'll stop reading. You can read it. Here's an example. So, x cubed minus 2x minus 3 divided by x plus 1. If I look at this, clearly the numerator is not the derivative of the denominator. However, it is an improper rational, so the logarithmic rule isn't going to apply anyway, because you have to have at least a proper rational, so where the numerator's degree is less. But you can convert any polynomial or any rational that's improper into a proper, well, technically a mixed proper, through polynomial division. Let's see how that would work out. So polynomial division is generally nobody's favorite method because it usually takes a while. It's very easy to skip over things like if you have a missing squared term, for instance, you need to add in 0x squared. And so from there, it takes a little while to work through. But the process isn't all that difficult. It just takes time and therefore usually isn't somebody's first method that they like to use. But let me work through it with you. So x cubed, what I need to do here is to divide the x cubed into the x plus 1. I decide what do I need to multiply x by to get x cubed. So that would be x squared. So I take my x squared, multiply it against the x plus 1. So x squared times x is x cubed. X squared times 1 is x squared. Now just like with long division at this point, we have to subtract these two numbers. X cubed minus x cubed cancels away. And that's exactly what we were aiming to do here, to get rid of this leading term. But do be careful in this next step, because it's now 0x squared minus x squared, which would be negative x squared. It's very tempting to just add those together, and that's generally where the crux of the problem comes from. So next, let's bring down the next term. Negative x squared minus 2x. The process repeats itself, and I ask myself, what do I need to multiply x by to get negative x squared? Well, it's negative x. So negative x times x is negative x squared. Negative x times 1 is negative x. Now I subtract. And again, negative x squared plus x squared, because that negative distributes, cancels that first term. Negative 2x minus a negative x would be negative 2x plus x, which is negative x, then minus 3. Okay, we're still continuing. So what can I multiply x by to get negative x? Well, negative 1. Negative 1 times x is negative x. Negative 1 times 1 is negative 1. We subtract here. The negative x's cancel this time, and I have negative 3 minus negative 1, which would be negative 3 plus 1, or negative 2. Now, what I can do is say that my original integrand is equal to the polynomial x squared minus x minus 1. So that polynomial plus the remainder of negative 2 over the original denominator. So this is called a mixed rational. So I have a polynomial plus a proper rational at this point. The polynomial is simple enough to integrate using the power rule. It's going to be x cubed over 3 minus x squared over 2 minus x. Now this next portion, take a look at this. I'm going to factor out that 2, leave the integral the way it is, and what happens next is the logarithmic rule applies. The denominator is exactly the derivative of the denominator is exactly the numerator, which means this is going to result in the natural log of the absolute value of the denominator. And I have my final answer. Now we need to look at some trig functions. So we do know some integrals involving trig functions, but they were all based off of inverses of derivative rules. We'd like to get integrals involving all the trig functions. We know a couple. For instance, the integral of sine is negative cosine, and the integral of cosine is sine. We know those integrals. But we need to establish these rules, like the integral of tangent is negative natural log of absolute cosine plus c, which on first inspection you might be thinking, where in the world does that come from? Well, I'll show you a proof, and it's actually not that strange. So for instance, if I try to integrate the tangent of x dx, and I'm just making it x for simplicity. This would apply if we threw the chain rule into it. I don't have any means of integrating tangent from the outset, but I do know some things about tangent. One in particular is that it is the sine of x over the cosine of x. And what's interesting about that is if I tried to do a substitution and let u be the denominator of that fraction, recall that the derivative of cosine is negative sine, which is pretty close to what you have in the numerator. It's only off by a negative, so negative du is sine x dx. So I can say negative. This is going to change into, so cosine gets replaced with u. Sine x dx gets replaced with du. Now, this is a logarithmic integral. So it's going to become negative natural log of the absolute value of what's in the denominator, which right now is u, but was originally, cosine. So this becomes negative natural log absolute of cosine x plus c. And that's the reason the integral looks the way it does. Its partner function is similar. The proof is extremely similar as well, so I'm not going to work through it. But we do have one other set of functions to look at. That's the integral of secant, which ends up being the natural log of the secant of u plus the tangent of u, which I'm not going to prove because it's not much different than the proof that I just gave you. It's very similar, in fact. And its partner function, the cosecant, is the negative natural log of cosecant u plus cotangent u. So I would definitely memorize each individual function as a group and just remember the partner functions as which one's negative and which one's positive. Let's see some examples with those. So first off, the secant of x over 3. So if I want to evaluate the secant, first thing that I need to do is do some substitution, because it isn't just the secant of x dx, it's the secant of x over 3. So I'll let u be x over 3, so that du would be 1/3 dx. On the outside of the function, I don't have a 1/3 multiplier anywhere, so I'll multiply both sides of this equation. That's a terrible u. I'll multiply both sides of the equation by 3, so that I can say 3 du is equal to dx. So this will become 3 times the integral of secant u du, which, based off of the rule we just established, would be 3 times the natural log of the absolute value of secant of u plus tangent of u plus c, and replacing back to the original variable, 3 natural log absolute secant of x over 3 plus tangent of x over 3 plus c. Next up, the integral of cosecant squared x minus 1 divided by the cotangent of x dx. Here, if we look at the denominator, it's clearly not the derivative of the numerator, but we may have to use some identities to reduce this in such a way that we can actually perform this integral. So one thing I do recall from trig is cosecant squared and 1 in certain conditions do reduce each other through the Pythagorean identities. I recall the one that is sine squared x plus cosine squared x equals 1, but I never really remember the one involving cosecant right off the top of my head. However, it's actually extremely easy to figure out, as long as you remember this one that I've just written, and the fact that cosecant is going to be 1 over sine. So I'm going to take everything in this equation and divide it by sine squared. So sine squared over sine squared is 1. Cosine squared over sine squared is cotangent squared x. And then 1 over sine squared is cosecant squared x. So now I've developed this rule that involves cosecant squared. But I don't just have cosecant squared in my numerator. I have cosecant squared minus 1. So I think I can even do better than that. So cotangent squared x would be cosecant squared x minus 1 if I just subtract 1 from each side. This then becomes cotangent squared of x over cotangent of x dx, and one of these factors of cotangent cancels out one of those in the numerator, leaving me just the integral of cotangent of x dx, and that we have a rule for integrating, which is the natural log of the absolute value of sine x plus c. Another example, this time involving a definite integral. So I want to evaluate the integral from -1 to 2 of 2x plus 3 dx. The way that I can do this is if I notice that having a rational function here generally indicates that I probably need to use a logarithmic rule, and that the denominator is really close to the derivative of the derivative of the denominator is really close to what the numerator is. That sort of helps me in the thinking process that that's the route that I need to go. So the denominator is 2x plus 3. Its derivative is 2 dx, or 1/2 du would be equal to dx. Then, since this is a definite integral, here's the thing. When I told you that if you do a definite integral and you change the variable of integration, you do in fact have to change the endpoints of integration. But if you don't actually change the variable of integration, you don't have to. So for instance, here I know that just based off of my means of evaluating logarithmic integrals, that this is going to be 1/2 of the natural log of the absolute value of that denominator. But I never changed my endpoints of integration or the variable of integration, so I'd still evaluate this from -1 to 2. You can certainly do the steps of substitution, change your endpoints of integration. It's fine either way, you'll get the same answer. But in this case, let's see what we get in the end. So 1/2 of the natural log of the absolute value. 2 times 2 is 4, plus 3 is 7, minus the natural log of, when I plug in -1, it would be 2 times -1, which is -2, plus 3, which is 1. And a couple of principles that are useful here. First off, natural log of absolute 7, same thing as just natural log of 7. And it's not a real number, so or I'm sorry, it's a real number, but it's not an integer or anything, or a fraction. So just leave it as natural log of 7. But then also, natural log of 1. There's a property of logarithms that says a logarithm of any base evaluated at 1 is equal to 0. So that term goes to 0. So the final answer here is just 1/2 natural log of 7.